Hello, in this video we will talk about canonical form of logic in the form of sum of product and product of sum, min term and max term. The methods of logic circuit simplification and design that we will study require the logic expression to be in a sum of product or SOP. Some examples of this form are A, B, C plus A naught, B, C naught. Each of these sum products expression consists of two or more n terms or products. They are OR together. Each n term consists of one or more variables individually appearing in either complemented or uncomplemented form. In the sum of products expression, in this expression, the first n product contains the variables A, B, and C in their uncomplemented or not inverted form. The second n contains A and C in their complemented or inverted form. In sum of product expression, one inversion sign cannot cover more than one variable in a term. For example, if you want to express A, B, and C naught, this is not sum of product. In every element in the n form is called min term. A Boolean function can be expressed algebraically from a given truth table by forming a min term for each combination of the variables that produce a 1 in the function and then taking the OR of all those terms. For example, we have two functions in here, f1 and f2. If the value of the output f1 is 1 in here, so that this is the min term part or the min term element. We can write as the input. Input x have a value 0 and y is 0 and z in here is 1. So we can write x naught, y naught, z in min term form. And next, x is 1 and y is 0 and z is 0. So we can write the min term as x y naught dot z naught. And then we have a value for the input x is 1 and the input y is 1 and the input z is 1. So we can write in min term form as x dot y dot z. We know in decimal, so we can write 000 as M1, 001 as
M0 and 001 as M1 and 010 as M2 and 011 as M3 and 100 as M4, 101 as M5, 110 as M6 and 111 as M7. This is for the midterm form in decimal. So F1, function F1 in here, we can write as M1 plus M4 and M7 because the output is 1 when M1, M4, and M7 in midterm form. So midterm is the part of sum of product. So the product is sum. The product, the product element is every element is summed by itself. So we can write x naught, y naught, x naught, y naught, and z as here, and we add all x y naught, x y naught and z naught, and or by x y z. So we can see in sum of product, we do product form first as a midterm, and we OR every element of the product form into one function. We do the same step for F2. We know this is the midterm form for the output 1. This is x naught, y naught, and x naught and y and z, and then this is x y naught z, and this is x y z naught and x y z. So we can write the function will be produce 1 as a value when M3 or by M5 and or by M6 or by M7. So we write the midterm form as in this Boolean expression. As we know, in midterm or next is a max term, we write all the input or the variable of our Boolean expression. This is we can say canonical form. This is a canonical form when all the variable in the Boolean expression we write full or completely. This is for the mean-term form. Next, the complement of F1 is read as we do F1 accent or F1 note. We can write the complement in here is this is the F1 expression. So if we do the complement, we can get this using the Morgan theorem. F1 accent or F1 not, the complement of F1. In the Morgan theorem, we know that x dot y naught is x naught plus or by y naught, and x plus y naught equals to x naught dot y naught. So we do this principle for our Boolean expression in F1. So the result in here is x naught, y naught, z naught, naught, dot x naught, y, z naught, naught, and dot x naught, y, z naught, and dot x, y, naught, z naught, and dot x, y, z naught, naught. So this is if we do this F1 function with inversion or the complement of F1. So we can write as x plus y plus z, because we not again, so the result is the original x, and this is the original y, and this is the original z. Dot, we can write in here x plus y naught, plus z dot x plus y naught plus z naught, and dot x naught plus y plus z naught dot x naught plus y naught plus z. So we can get F1 complement like in this expression. So we can write as M0, M2, M3, M5, and M6. Why? Because this is the max term form. And we do the same for the F2. F2 in here is, we know the result is M3 or M5 or by M6 and or by M7. So we can do as the same step for complement of F1, and we do for the F2 expression. So the result is M0, M1, M2, and M4. For what? Because in min term, this character of this min term is M for the lowercase, and the max term form we can write as M in uppercase. And the decimal digit, this is from the the binary form of the input. So in max term, we know that in min term we know that 0, 0, 0, or in min term is M0, and in max term we write M0. And then for the Boolean expression for this binary, in min term we write as X0, Y0, and Z0. But in max term form, we write as X plus Y plus Z. So if the input is 0, we write the variable for the uncomplemented variable or the uncomplemented input. So if X is 0, we write as X in max term. And Y is 0, so we write X or by Yao. Yao because Yao is 0, so we write as Yao with uncomplemented variable. And Z is 0 in here, so we write Z as an complemented variable for the max term form. In this third table, we can see that this is the max term and min term for 3 binary variables. So as we can see in here, M0 for min term and M0 for the max term, and until the M7 for the min term is, we can see the term we write X Yao Z. And for the max term M7 with uppercase, we can write X naught or by Yao naught or by Z naught. Because in max term 1 is right without uncomplemented variable. Right by uncomplemented variable. So we see that this is X naught or by Y naught or by Z naught. So min term, product term in sum of product, and max term is sum terms in product of sum. Standard forms of SOP, SOP, and POS can be derived from truth tables. And we can see if we have the truth tables like this. In min term form, we take from the output 1. So we can write as min term form as the product terms in sum of product. So this is the output is 1, so the min term is A naught, B naught, and C naught, and C. Sorry. So we can write A naught dot B naught dot C. And again, this is the output of Z. This Boolean expression is 1, so we can write A dot B naught dot C. And this is again next is A B dot C naught, and this is A dot B dot C. So this is the product terms in sum of product. So we can write as Z equals to A naught dot B naught dot C, or by A dot B naught dot C, or by A dot B dot C naught, and or by A dot B dot C. And we can write the min term symbols, or like in this truth table. This is M1, and this is M5, and this is M6, and this is M7. So we can write sigma M1, 5, 6, and 7. This is the symbol for sum of product. We can use sigma. And for the post form, we can take the expression from the output if the output is 0. So this is the min term form, the max term form. We can take from this, because the output is 0, so we write A or by B or by C, and this is the input. A is 0, B is 1, and C is 0, so we can write A or by B naught or by C. And next we can write A or by B naught or by C naught, and then A naught or by B or by C. So we can write the product of sum form as A or by C or by B or by C by product form. Product form in here, so we can get the we can get the post form, and we write with P of the max term M null, M0, M2, M3, and M4. So for the post form, we write P, M0, 2, 3, and 4. This is for the max term and post form. So all the Boolean expression can be converted to the two standard form of sum of product and product of sum. Standardization of Boolean expression makes evaluation, simplification, and implementation of Boolean expressions more systematic and easier. So again, we resume this the mean term form or the product form for the SOP or sum of product, and every digit in mean term we call it literal. The mean term was a sum. Defines the Boolean function are those which give one of the function in a truth table, or the output is 1. So we can write the sum of product expression. And then we recall again, this is not SOP or not sum of product because B and C is in uncomplemented in one way. So in SOP, we write the standard SOP forms that contain all the variable in the domain of expression for each product term. So every digit in this mean term have an uncomplemented element, independent variable. So and then we can write the canonical sum of product with complete variable in our domain of the Boolean expression. So if we have 4 variables in our Boolean expression, this is the canonical form or the standard form for the sum of product in product term of SOP. So we have to write complete variable in product term of sum of product. Okay. To convert SOP to its standard form, we use the Boolean rules A plus A naught equals to 1, and A dot B or by C is or equals to A dot B or by A dot C. So if we have the Boolean expression A dot B naught dot C naught or by A naught dot B naught and or by A dot B dot C naught dot D, so we have to analyze what the product term is missing in what variable. So the first term, because this contain 4 variable A, B, C, D, so in the first product term, we analyze that they don't have d variable, and then the second form, the second term, the product term, they don't have c and d variable, and this is the complete variable. So the first product is missing a variable d, and the second is c and d. So we apply d or by d naught equals to 1, and c or by c naught equals to 1 for first term and the second term. So we write as a dot b naught dot c dot d or by d naught, and a naught dot b naught or by a naught dot b naught dot c or by c naught dot d or by d naught or by a dot b dot c naught dot d. And we apply the distributive law, so we can get a dot b naught dot c dot d or by a dot b naught dot c dot d naught, and or by a naught dot b naught c, a naught dot b naught dot c naught dot d plus or by d naught or by a dot b dot c naught dot d. And then we can get a naught dot b naught dot c dot d and a naught dot b naught dot c naught dot d naught as in here. So this is the standard sum of product form. Next, we talk about mean-term expansion. In the slide before, we have the expression of f. So we can from the truth table, we can write the expression for f is with the output is 1. So we can write this expression a naught dot b naught dot c and or by a naught dot b dot c or by a dot b naught dot c and or by a dot b dot c naught and or by a dot b dot c. And we can build f complement from the output f in here 0, so the f accent or f naught is 1, and then it's become 0, it's become 1, it become 0 again, and from 0 to 1, and 1 from for f1 become 0, 0, 0. So f accent or f naught in here we can write from the output is if the output of f accent or f naught is 1. So this is the result. A naught dot b naught dot c naught or by a naught dot b dot c naught, and then or by a dot b naught dot c naught. So this is the mean-term expansion for the for this from the truth table. Variables appear exactly once in its mean term in true or inverted form, but not both. So this is the notation of mean theorem. So if we have canonical form for f a b c, we can write if we have sigma m 1 3 5 6 and 7, we can write m1 or by m3 or by m5 or by m6 and or by m7. So m1 is a naught b naught c and m3 is a naught b dot c and m5 is a dot b naught dot c and m6 is a dot b dot c naught and m7 is a dot b dot c. The canonical form to the minimal form, so we can write as a dot b or by c. We can get this from the minimization of this expression Boolean, this Boolean expression. So we use Boolean algebra for example b plus b naught is 1, and then we can use this principle to reduce this Boolean or this expression. So you can try it. For product of sum, this is the max theorem term and this is the literal. And in POS or POS, a single over bar cannot extend over more than one variable. So this is not POS because B or by C is extend over one variable. The standard POS must contain all the variable or the variable in the domain of the expression for its sum term. Now, for example, we can see this is the complete max term form, and it combined with product. So this is the product of sum form, but not in standard, because same as SOP in POS, every max term must contain complete variable or all the variable must write it. So we can see the first sum term is missing the variable of D, and the second sum term is missing A. And this is the complete form of sum term. So with the Boolean rules A dot A naught equals to 0 and A plus B dot C as equal with A or by B dot A or by C. So we can apply D dot D equals to 0 in first sum term, and the second the second sum term, we can add A dot A naught. So we can expand first and the second terms with A or by B naught or by C or by D, from this to this, and A or by B naught or by C with or by D naught, and can write A plus B naught plus C plus is same with or by, I say, and A naught plus B naught plus C plus D naught, and this is the and dot A plus B naught plus C naught plus D. This is the standard POS form, product of sum form. For example, we have the function is f equals to x dot y plus x naught dot z. So we can write as x dot y plus x naught dot x dot y plus z. And then we can write x plus x naught dot y plus x naught dot x plus z dot y plus z, because x plus x naught is equals to 1. So we can write these three of some term. So because of the function has three variables, each OR term is missing one variable. Therefore, for x naught plus y, the missing variable is x plus y. So the missing variable is z, and x plus z, the missing variable is y. So we add y dot y naught, and y plus z is equals to y plus z plus x dot x naught is equals to x plus y plus z dot x naught plus y plus z. So this is the result from this expression. So we write as x plus y plus z, because this is the same form. We know that x dot x is x, so we can write 1 in the product form, and then dot x plus y naught plus z, and dot x naught plus y plus z. This is same to so we can write this original expression of Max theorem, this Max theorem, x naught plus y plus z dot x naught plus y plus z naught, because this is 0, 0, 0, and this is 0, 1, 0, and this is 0, 1, 1, and this is 0, 1, 0. So the result is M0, M2 is M2 for 0, 1, 0, and M4 for oh sorry, oh yeah, this is not M4 but M3 I think, because 0, 1, 1, 0, 1, 1 is M3, and 0, 1, 0 is M5. M5. Oh, sorry. This is 1, 0, 1. 1, 0, 1 is M5. Okay. This is for to how to get the standard form of product of sum. And for the product of sum in canonical form, we can do Max theorem expansion as in sum of product. So, in the with the same truth tables, we can write the product of sum for the if the output of f is 0. So we can write the Max theorem for this every element. This is A dot B dot C, and then this is A plus P naught plus C, and this is A naught plus B plus C. So we can write for the product of sum as in here. So we can do F accent or complement of F. The output, if the output is 0, so the output for the complement of F is 1, 0, 1, 0, 1, 0, 0, 0. And we do as the same for the output of F accent or F complement is 0, so we can write in here, 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 and here. For the last, A is 1, B is 1, and C is 1. So we write A naught plus B naught plus C naught. So we do same for the other of sum term in product of sum. So we can get the F accent or the complement of F in the product of sum canonical form. So this is the same for the notation in max theorem. For the product of sum, we can write the canonical form using P and M in uppercase. So if we have a canonical form in product of sum for 0, 2, and 4, we can write M null or M0 dot M2 and dot M4. And then we can write the M null as A plus B plus C, and M2 as, because this is 0, 1, 0, so we write in max theorem as A plus B naught plus C, and for M4 is 1, 0, 0, so we write as A naught plus B plus C. So we can get the product of sum of this F Boolean expression. And from the canonical form, we can get the minimal form using Boolean algebra, or we can use A dot A naught A dot A is A, for example, using the Boolean expression law. So you can try by yourself for this, how to minimize or how to minimization, how do the minimization for this expression. So for the canonical sum of product, we do N and then sum by OR. And for the canonical product of sum, we use OR gate and then AND gate for the product of sum. So if we want to convert between canonical form, min theorem to max theorem, use max theorem that aren't in min theorem expansion. So if we have A, B, C, for this Boolean expression, so the min term form is write by sigma of M 1, 3, 5, 6, 7. We can write the max theorem from the output of 0. But this is not min theorem expansion. So the order of min theorem is max theorem with output is 0. And max theorem to min theorem, use min theorems that aren't in max theorem expansion. So if we have the max theorem 0, 2, and 4, so the min theorem is 1, 3, 5, 6, and 7. The min theorem of F to min theorem of F accent or complement F, use min theorem that don't appear. So if we have the sum of product 1, 3, 5, 6, and 7, so the complement of F is 0, 2, and 4. But we still use sigma. That sign, this is the sum of product form. And max theorem of F to max theorem of F accent or F not use max theorem that don't appear. So if we have the product of sum 0, 2, and 4, so the complement of F is max theorem PM max theorem 1, 3, 5, 6, and 7, because this don't appear at the F function. So this is the conversion between canonical form. And for the SOP or sum of product and product of sum and the Morgan theorem, we can see the relation. If we have a sum of product F accent or F naught is A naught dot B naught dot C naught plus A naught dot B dot C naught plus A dot B naught dot C, we can apply De Morgan to get product of sum form. So we do the, because of this have a complement, so we can write A naught dot B naught dot C naught plus A naught dot B dot C naught plus A dot B naught dot C naught
And we can write as this. So apply De Morgan to get pos. We can write as A naught, B naught, C naught, naught, because this is from the Morgan theorem. And dot A naught, B, C naught, naught, and then dot A, B naught, C naught. Using or, because this is from the Morgan theorem. So we can write as A plus B plus C, and then dot A, because A not and not, and here is A, plus B naught plus C not, and we not again, so we can get the original form. And dot A naught plus B plus C as right in here. So product of sum of F naught is we have product of sum form in the for the complement of F, for example, like this, and then we apply De Morgans to get sum of product, same as in the sum of product to we convert to product of sum. So if we have just F in sum of product or product of sum, so if we want to convert from the sum of product form into the product of sum, so we can do F with
twice not. Or we can convert, or we can say that to convert from SOP to POS, or POS to sum of product. So we do not twicely. From if we have just from F, and or we can say we do the complement first and we do the not again, or we do complement again. So this to convert from the sum of product or the from product of sum into product of sum form, or into sum of product form. So if we have a function with sum of product, the mean term is 1, 4, 5, 6, and 7. So the complement or the f naught of this function is 0, 2, and 3. Or we can write M0, M2, and M3. And we take the complement of f naught by the Morgan theorem, so we can obtain f in a different form. So if we have M0 plus M2 plus M3 naught, so we can get M0 naught dot M2 naught dot M3 naught, or we can write as max term 0, 2, and 3. So we can write as P 0, 2, and 3 in the product of sum form. So example, in here we have an product of sum of product with the mean term 1, 3, 6, and 7. So this is the mean term. We can write the decimal symbols 0, 0, 0 with 3 input x, y, and z, and 1, 2, 3, 4, 5, 6, 7. To easier the decimal symbol make easier to us to write the number of mean term or the number of max term form. So in mean term we have 1, 3, 6, and 7. So the max term we get from the 0 output. And then we can write as P for the max term M0 or M0 and M2, M4, and M5. The conversion between canonical form. So for example, in here we have F1 as sum of product. Sum of product in here, this we can write y naught and then x dot y, and then plus x naught, y, and z naught. And then we can write, for example, in here we have function f2, and we can draw the circuit as using as in picture B, using OR and and with and gate. And then this is for F3. We have A dot B dot C dot D dot E. So this is the circuit for F3 in the form of this Boolean expression. We need two gate and two gate or gates. So this expression we can write as A dot B and then C dot or by C dot D and or by C dot E. So in here we need 3 AND gate and 1 AND gate or AND OR circuit. AND OR circuit is for sum of product. And if we have a product of some form, so we can call it OR AND circuit. Okay, next. How to design interim and or logic. So this is the sum of product. We know that the canonical form of sum of product, we must write all the variable or all the input for every element of midterm. So we draw this midterm using AND gate. This we need 4 AND gates and we do the OR the adding function for the SOP. Using OR and OR logic, and we also known as two-level logic. Two-level logic is because this is first level and this is the second level. Okay, and if we want to design midterm using just NaN, so we can apply the Morgan theorem to get all the NaN logic. Because of the Morgan theorem, if we have Z equals to P naught ORed by Q naught ORed by R naught ORed by S naught, so using the Morgan theorem, we can write as P dot Q dot R dot S naught. We can not for every variable in here. So if we have applied this to the Morgan using the Morgan theorem, so we can apply NaN logic. So I will try to apply it by the Morgan theorem. A P naught C plus A B C naught plus A B C, and we do the Morgan theorem so we can get and then dot A naught plus B naught plus C dot A naught plus B naught plus C naught. So this is the form. Sorry. Okay, this is for the Morgan theorem. If we convert to the another form in the Morgan theorem, so we can apply this for the NaN logic. Actually, this is just for the using this theorem. We can apply it using NaN and NaN logic. Just for this. Or we can write like this. Dot A, B, C, not, and dot A, B, C, not. This is the form of this Z. So if we want to get this is the end form. If we get the form of this expression using the Morgan. So if we not again to get the Z, the form of the Z expression. So we can do in every theorem using NaN, and then we not again because the illustration is Z not, and we not again, so we get the original Z. So if we do NaN not again, so the output of every NaN in here become an input for the NaN gates. Okay, this to design min theorem using NaN and NaN logic. And how to design max theorem or N logic? We can draw the circuit. This is using OR, and this is using OR again, and this is using OR again, and this is using OR. And then because this is the dot product, so we need an key. Sorry. Okay, using the Morgan theorem too, if we have z twice, not twice in here, so if we write z is likely a plus b, the first knot in here, ab plus c knot plus a plus b knot c knot plus a plus b knot plus c knot plus a knot plus b plus c, and then knot. This the implementation is using NOR. So this is using NOR. And then if we take the second knot, so we can use this knot using NOR again. Okay, this for NOR and NOR logic for the max theorem. This is the summary realization of combination logic using NAND and NOR. This is x dot y, so we can get the NAND using the Morgan theorem, because x dot y naught is equals to x dot y naught. And then if we have x naught or by x or by yaw naught, so we can write or with inverted input in the x and yaw. So this is same as x naught or by yaw naught. And this is the equals to based on the Morgan theorem is same as x or by y or by yaw naught, and all of this mean term is to the complement. So we can write as NOR gates. This is NOR and this is NOR too. And x OR by y naught is equals to x naught dot y naught. So this is x naught dot y naught. So it's same with x plus y naught is equals to x naught dot y naught. This is NOR too. NOR. So we can write x No, this is not nor. So this is not nor. X dot e naught is same with x naught plus e naught. This is using nor and this is using nan. So this is nan. This is not nor, sorry, this is nan because x dot y is same with x naught or by y naught. So we can write nan is equals to or with, sorry, or with inverted input is nan, and nor is equals to nan with inverted input. This is the use of the Morgan theorem to do combination logic or to realize the combination logic. So this is the using nan and nor again for the realization. This is the inverter, nan for nan. So this is x naught and we have from the nan with not in here, and we have or using this not x naught dot e not, and this is for the or. This is from x naught dot e naught if we want to use just nan only. So or we can draw OR gate using nan. This is for x naught with the both of the input of nan is become 1 or just x, and this is both of the input connected, so we can get the yellow as an input. So this NOT gate is the NOT gate, and we do NOT again in here, x naught dot e naught, and we do the NOT in here. NOT is same with x naught plus y naught. So the result is x ORed by y. And then for the or if we using nan, so this if we using nor with the input is connected, the both the input is connected, so we can get NOT gate, and then a, and then we And this is for NOR with both the input connected, so we get not from NOR gates. And for AND gates, we can build this gate into from the NOR gates only using the Morgan theorem. X naught or by Yau not, so we can get x dot y because this is same as x dot y not, and we do not again, so we get x dot Yau. So this is for not x because this is not gates from NOR gate, and this is Yau not, and then we do not again in here using NOR, and we can get the AND gates from NOR only. And then for OR, we can build this gate using NOR and NOT, so we can get X OR by Yau. This is the summary if we want to draw the combinational logic using NAND only or NOR only. And we do the next slide about combination circuit analysis. Obtaining a formal description of each logic function. Why? Because we determine the behavior for various input combinations, and to manipulate an algebraic description to suggest different circuit structures and transform a description into a standard form, and then use the description in the analysis of a larger system. So, for example, we have this circuit with 3 input X, Y, and Z. And then if we have the sequence of logic, binary logic, like 0, 0, 0, 0, 1, 1, 1, 1, for example, and then Yao is 0, 0, 1, 1, 0, 0, 1, 1, and we do the inverse this input, so the result is 1, 1, 0, 0, 1, 1, 0, 0. So if we use OR in here, we can predict the output or the result. And then 0 OR by 1, and the result is 1, until 1 or 0, the result is 1, 2. So we do this for another gate, and this is for the N, first and second, and then this is the first OR and the second OR, and this is for the NOT gates. The signal expression, so from the circuit, we can write the Boolean expression. This is X OR, because OR, so the function is add, and then because there is a NOT gate in here, so the result is Yao NOT, and this is X NOT, and this is the Z NOT. And then we do X plus Y NOT dot Z, and we do X NOT Yao dot Z NOT. Then we can get F equals to X plus Y NOT dot Z plus X NOT dot Y dot Z NOT. from the second gates and gates. So from the Boolean expression, we can write as x plus y naught dot z is same with x dot z plus y naught dot z, and this is same x naught dot y dot z. And next, these two level and r from the another expression, Boolean expression. This is the circuit. We have new circuit with the same function. So this is for x dot z, and this is for y naught dot z, and this is for x naught dot y dot z naught. And we get together using OR gates. This is a faster course, but costs more. And this is the signal expression 2 for the first form of the Boolean expression. So if we want to convert this expression into product of sum, so but not product of sum, but AND out logic function, so we can do this. So we can get x dot y naught plus x naught dot x plus y naught plus y and then dot x plus y naught plus z naught dot z plus x naught dot z plus y dot z plus z naught, and this the result is 1 dot x plus y naught plus z naught plus dot x naught plus z dot y plus z dot 1, because this the result is 1, and this the result is 1, and the result this is 1 too. So the result is x plus y naught plus z naught dot x naught plus z dot y plus z. And for the two level or n, we can get this for or n, or in the not canonical, but this is the form of product of sum. So we do or and circuit. So this is the realization of this combinational logic function. And another example, this is for the expression, the Boolean expression with w dot x not because this is the second not dot y not again, and then w not plus x plus y not and w plus z not, and we combine with nor in here. And I want to, yeah, okay. So we can substitute this gate or the symbols using the Morgan theorem, because we w dot x not it's same with w dot x not in here is w plus x w naught plus x naught, so or w naught plus x, so we can substitute the symbol then using or with this is nan and this is nan too, because both of the input is not. And then this is nor, so we can substitute the symbols of gates using nor too. The different circuit with same function, this is x naught, w naught, and y naught. This is, we can write like this, because in the last gate, in every inputs have not, because have not, so this is meet with not in every output of this gate, and I notice with red line or red cycle in here. So we can make this disappear or not because not it meet with not meets with not, so the result is not complemented. So we can write the symbols like this and these two. But if this is not, this circle is disappear, so this kit is not nan kit. So we just, this is just a buffer, just like a buffer, but we don't make it disappear, because this is the form of another form of nan kits. This is the circuit is different but have a same function. So if the combinational circuit analysis is, we analyze the circuit first, or combination circuit analysis is we do the from this. Okay, for example, analysis, if we have a circuit first and we analyze the Boolean expression. What is the Boolean expression of the circuit that we have? So this is the combinational logic analysis. And then now we will talk about combinational circuit synthesis. So combinational circuit synthesis is start from the logic expression or the truth table. And we can manipulate the expression if necessary. And we have to build a circuit from the expression. It's for combinational circuit synthesis. A circuit realizes an expression if its output function equals that expression, and the circuit is called a realization of the function. So, if we have a 4-number input with the notation is n3, n2, n1, and n0 or n0, this function produce one output for n 1, 2, 3, 5, 7, 11, and 13, and produce 0 for otherwise. So we can write the truth table for the canonical sum or sum of min theorem like this. This is the number that produce output 1, 7, and then 11 and 13. So we can write like this. This is 4, 1, 2, and 3, and this is 5, and then this is 7, and this is 11 and 13. So this is for the canonical sum. Can write all this using and then the last is using or. To analyze procedure, to obtain the output Boolean function from a logic diagram, so we have F2 as a dot b plus a dot c plus b dot c, and T1 is a plus b plus c, and T2 is a dot b dot c. Outputs of kids that are function of already defined as symbols. T3 equals to F2 dot T1, and F1 equals to T3 plus T2. So to obtain F1 as a function of A, B, and C, we form a series of substitution as follows. So this for the F1 is equals to T3 plus T2 is equals to F2 naught dot T1 plus A dot B dot C. So at the end of the result, we can obtain A naught dot B dot C naught plus A naught dot P naught dot C plus A dot B naught dot C naught plus A dot B dot C. Because this is for the F2 naught, and then this is T1, and we use the distribution function for A, B, and A plus B plus C, and here F2 and T1. But before we do this dot product, we do not in here using the Morgan theorem. So A dot B become A naught plus B naught. A dot C become dot A naught plus C naught, and B dot C becomes B naught plus C naught. And then we do the distribution law for this min theorem. So we can get A naught plus B naught dot C naught because of this. And then B we do this and we get A dot B naught plus A dot C naught, and then plus B dot C naught plus B naught dot C, because C naught dot C is 1. It's null. And B dot B naught is null too. Okay, so from this we can get the use the distribution function again. So we can get A naught dot B dot C naught plus A naught dot B naught dot C plus A dot B naught dot C naught and plus A dot B dot C. And this is the circuit to realize this Boolean expression. So this is for F1 and this is for T3 and this is for F2. And we can get the truth table as this. For every output, F2, T2 and T1. So this is the truth table, and this is the resum. Literal is a variable or the complement of a variable, and product of term is from or dot product expression. This is the example, and sum of product expression is some like z plus x naught dot y plus x dot w dot y naught, and this is the sum term. And product of sum expression, we do sum as the expression, and we do dot for the to get this max term together, or this element together using the product expression. And this is the normal term, and min theorem with n variable is normal product term, and max theorem for n variable is normal sum term. Other representation, the min theorem list is on set its min theorem turns on the output for exactly one input combination. So for the min theorem list, we have to remember that in sum of product, min theorem that write as expression is must take from the input, which is produce output as 1 or equals to 1. So the min theorem will write as x naught dot y naught dot z naught, and this is the min term 2, we can write x naught dot yao dot z, and then we can write as x dot yao naught dot z naught, and this we can write x dot yao dot z naught, and we can write x dot yao dot z. And for the max theorem list, its max theorem turns off the output for exactly one input combination. So if we want to get the max theorem list, we take from the input which produce 0 as an output. So we can write as x plus yao plus z naught. And the second, because the output is 0, so we can write the max theorem as x plus yao naught plus z. And then this is max theorem 2. This is x naught plus yao plus z. I say plus is same with or by. This is the z is equals to 1, so we can write z naught. So this is for the max theorem list. We can take from the truth table with the output is 0. And the last representation for a combinational logic function, we can write as truth table, and we can write the expression as canonical sum. Canonical sum means that you have to write all the variable in the function completely. So if you have 3 inputs as x, yao, and z, for the canonical, you have to use this input, write as min theorem list or min theorem element for the sum of product, for example, in the complete input, all the variable in every min theorem. And then min theorem list is, the symbol is sigma, and the number is min, it means representation of the min theorem list. And then the canonical product, using max theorem form and using dot product to combine in every max theorem. And the max theorem list, we use symbols p, and the number in here express max theorem list. So this is the end of our video. Thank you for watching this video. See you in the next video. Thank you.